Welcome to your first day on the job, and your boss walks up and says, "Hey, you, make me a buffer with a pH of 3. Well, you have to know that pH or you can't do it at all. So I guess that's step 0 in doing this. In fact, let's list those steps out from a previous video. Things that you need to know. So, 1, target pH. And that's 3.00. You have to know that. 2, it would be nice to know the application. And that'll come into play with toxicity and things like that, but it will also come into play with your buffer capacity and things like that. So at the very least, we would need to know like toxicity considerations and capacity. Now, you can kind of fake it if you don't know any better, but you just pick something that's very, very non-reactive and something that is a really, really high buffer capacity. But then that comes into play with cost and everything like that. And then the third thing that you don't actually need, in fact, I'll put this in red or something, you don't actually need the volume. All right? For a buffer system, volume doesn't matter. All that matters is the ratio of the weak acid or base and its conjugate. And then as you dilute it, the pH won't change. It's kind of slick, and we'll look at how that works. So in the previous video, we had discussed these considerations to take stock of. The first one being the target pH. Okay, and we've got that. Check. 2, in looking at our buffer system, we're looking for availability, cost, and reactivity, right? A source and how toxic or reactive it is. And then 3, we were looking at a solubility. And so what I've done is printed out enlarged version of a part of a Ka table. So your starting point would be to grab some Ka table and work from there. And I happened to pull a chunk out of, I think, this one. I don't remember. This is one from Coates and Treacle. Anyway, I zoomed in and I pulled up some other information from online so that we could go through these steps as we need to. So we're going to start right there. I have a target pH of 3. Our goal is going to be to find some acid where the pKa is equal to or close to the pH, which in this case is 3.00. So let's look at this list. Nitric acid, it's a strong acid, not a good buffer at all because you need a weak acid. pK is not even close anyway. Not close, not close, that's not bad, and then we're getting a little worse and a little worse and a little worse. So not knowing anything else, I'd probably try to grab this HF system. All right, target pH, it matches very, 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 very well. So next, let's take a look at cost, and I've got that one right here. As far as cost goes, it's about $11 per gram, which isn't too out of line with these other ones. It's tied for second most expensive, I guess, or third most expensive, but it's really not too cumbersome in that regard. So cost seems okay. And then if we look at availability, it's actually pretty hard to get hydrofluoric acid in any concentration. NaF you can buy, but again, there's another huge factor, which is toxicity for HF, which is 100 milligrams per kilogram of body weight. And again, I pulled these numbers just from somewhere online. They may not be super accurate, but it's clear to see that if some things are greater than the thousands of milligrams per kilogram, and if sodium fluoride has a LD50 of 100, the LD50 is just the mean lethal dose for half the population or whatever. That's not super important as long as you realize that that's a pretty small number relative to the other ones. So the only other thing I guess I would look at here is solubility. And again, comparing to these other ones, the solubility of sodium fluoride is 40 grams per liter, which is super low. So in terms of our first option, pH was pretty darn good. 3.14 is really close to 3. In terms of availability, it's not that available, and it happens to be pretty toxic, and it happens to be pretty insoluble. So that one is not going to be a good choice for us. In fact, HF's pretty dangerous. So we'll go to our next best case scenario, which is this nitrous acid, HNO2. And I'll be honest, when I first made this example, I chose HNO2 until I looked at the actual numbers. So option 2. All right, HNO2 is comparably priced to the HF, so that seems reasonable so far. Our pKa value is not ideal, but it's not horrible. It's not as bad as that one, at least. And then if we start to look at some of the other considerations, like the LD50, the LD50 is really close to HF. I was surprised by that, but that's a surprise of my own ignorance, not a surprise of reality. So 150 milligrams per kilogram. So automatically, sodium nitrite is not going to be a great choice. It's not super expensive. And in terms of solubility, it's got great solubility. So, well, I mean, it's pretty darn good. So if you look here, target pH, not great. Availability, not great. Cost, pretty okay. Reactivity, it's pretty toxic, so we probably don't want to work with that. Solubility is great, though. So that's another one that we're going to have to cross us off of our list. Now we're getting to some really not ideal buffer systems, and I'm sure some of you keyboard buffer warriors out there are like, oh, there's plenty of other better systems. These are the ones I'm listing. I'm sure there are better ones. I just happened to pull a chunk out of one of those tables. And this is a real-world situation. Formic acid, 3.74. It's 0.74 off instead of 0.78 off. So phosphoric acid, which triprotic acid, that might end up being a great option. But let's look at our formic acid here. First up, 3.74, target pH. That's not that great, all right? Second up, cost. That's one of the, well, the most expensive one on our list. But again, not necessarily prohibitive, $15 per 100 gram. If you're wondering where these numbers came from, they came mostly from eBay, maybe Amazon as well. So price at the higher end, pH, not great. Solubility, one of the better ones, so that's good news. And then LD50, 11,000. In fact, looking at these things here, that's probably the least toxic of all of our options. So everything's a compromise, and in this particular case, we're going to compromise based on toxic, not very soluble. So even though they had better pHs, we're going to go with that formic acid. Choosing a specific acid may feel like an overwhelming situation, but it turns out that the real magic and the real frustration comes in you having to pick up buffer capacity. But all of those things are going to be based on one specific ratio. So that's what we need to find out right now, how to apply this target pH of 3.0 to our formic acid system, which has a pKa of 3.74. So first up, I want to write out our generic K expression, HA, H2O, H3O plus, and A minus. For our purposes right here, we said we're going to use that formic acid system, which is HCO2H, and we'll just throw in here and that is what we're looking for in terms of our HA, our weak acid, and our A minus, our weak base. Okay. The Henderson Hasselbalch is where we'll start, and the Henderson Hasselbalch equation says that pH is going to be pKa plus the log of whatever our amount of A minus is over our amount of HA. And there's a bit of hand waving going on that I may as well mention, which is I didn't put concentration of A minus over concentration of HA, although that is technically true. Since they're in the same solution, they have the same volume, and those volumes cancel out, which is another advantage of this. It removes the need for molarity. You can just plug in moles or molarity or whatever. Best case scenario is this and this are the same, so that we have a maximum resistance to shifts in either direction. That's not the case here. We do have a target pH, and one of the things I preach to my students is write an equation, use it as a checklist. We do have a target pH. We do have a pKa, and that pKa is the negative log of our Ka value, 1.8 times 10 to the minus 4. All right, and that Ka value happens to be 3.74. And then we don't know HA and we don't know A minus. This is a linear algebra problem where you have two unknowns in one equation. And that means it has an infinite number of solutions. And I think that's where people run into the wall on how to do this stuff. So we're going to address that as we go here. But this is what I'm trying to solve for. And we can wave our hand at this and say, okay, I have this because it's our target. I know this because it's a constant. And I need to calculate ratio. All right, I'm not solving for one of the numbers, I'm solving for the ratio. So we can do some rearranging here and just say that if we want to solve for that ratio, A minus over HA, our A minus over HA is going to be 10 to the pH minus pKa. And for our purposes here, that is HCO2 minus over HCO2H, and that's going to be 10 to the 3.00 minus 3.74, which equals 0.182. That is a very, very, very important number because that is our target ratio. Whatever we do has to give us that. And so this is a 0.182 to 1, and that's our ratio of HCO2 minus to HCO2H. And that's a mole ratio, or, well, it's probably the easiest way to think about it. This. If there's one thing on this page that's absolutely critical, it's this 0.182 number. And like I said, that is where you get stuck, because if I have an infinite number of possible solutions to this linear equation, how do I pick one solution? So let's write some version of those words, and then we'll address it more specifically. Any combination of HA or A minus to HA that gives a ratio equal to 0.182 will work. Right? And this is volume independent. Okay? Volume won't affect anything. The only things that'll matter are those amounts, and do they end up with that ratio? Because if you dilute it, they're both in the same solution, those volumes cancel and you're right back to moles. So that's something that may not be obvious about buffers, but dilution does not change pH for a buffer. So this is the information we have. I paused for a moment there so I could set this table up. We need this ratio, and I'm just going to keep pointing at this because that's all we need. And there's an infinite number of possible solutions to get us a 0.182 to 1 ratio. And I want to look at some possible options, and we'll talk about the pros and cons of those options. So to get that ratio, every single one is going to end up with 0.182 to 1 ratio of our HCO2H, that's moles, and moles of our conjugate, HCO2 minus. So I calculated all these numbers in advance, and they all, I just slammed them into a calculator and solved the equation. And so here are some options that I had. How about 0.182 moles to 1 mole? Or, picking some stranger numbers, 0.091, just cut that in half, to 0.5. And that one I think is pretty intuitive. You can go the other way and say like 0.364 to 2, but you're not limited to integer multiples, so you could do something like 1.165 to 6.4, or 314 to 1725, or maybe something super small at the other end, 0.0015 to 0.00824. So let's look at some of these considerations. First of all, we had mentioned the idea of solubility. And formic acid happens to be pretty soluble, but probably not this soluble, 314 moles to 1725 moles. And then the other disadvantage would be cost on that. So I'm going to cross this one out. for reasons of solubility and reasons of cost. All right. One of the things we said it would be useful to know is the capacity, how much you need. And if that's not specified, then you kind of have to make one up based on cost and solubility, I would say. You don't want to go to the end of the solubility because that may be super expensive. This one right here may not be unreasonable in terms of solubility. In fact, I think you can saturate a sodium formate solution around 14.3 molar. So just as a little side note to us, 14.3 molar is the 970 grams per liter. So you could probably do this, but that's probably going to be pretty expensive. If you don't need it, don't do it. Something like this may be too small unless you're working with tiny, tiny amounts, so your capacity may be too low. And so we'll look in this range. I'm going to pick something that's fairly in the middle and not actually one of these numbers. I'm going to base it on my imaginary application capacity. All right. We've already picked the formic acid system, so toxicity is no longer a factor. I'm worried about how much I can use, so that will require a new page.